Hello everybody, we are doing section 3.5, the derivative of trig functions. This first theorem, we've already covered that one there. Sine x over x as x goes to 0. That is a result of the squeeze theorem. And then this is a new one that you just have to memorize. The limit as x approaches 0 of cos x minus 1 over x is 0. So we're going to do examples of this. The first one is kind of tricky. You got to be careful. So that approaches 0 and that approaches 0. And people say, oh, therefore it equals 1. But these have to approach 0 in the same way. That x and that x both approach 0 in the same manner. But that's a 4x and that's a 1x. So they're not the same. They're not approaching 0 the same. So you can't apply this theorem unless they're the same. So you might say to yourself, I wish I had a 4 right there. I really, really wish I had a 4. And by now you realize you can get a 4 there if you multiply by 1. There's my 1. And I will use my theorem of limits. If I have a constant, I can pull it out in front. I'm going to take that 4 out in front, and I'm going to leave the rest together. And you will get this. Now, that's approaching 0 and that's approaching 0. And they're approaching 0 in the same manner. So it doesn't matter if they're not x's, as long as both of these approach 0, which they are, and they're both approaching the same way. So that answer will be 4 times 1, which is 4. Now the second one's a little trickier because you need x's on the bottom, and there aren't any x's. Guess what the secret is? Multiply by 1. There is my 1, and that will result in this. It's going to be sine 3x over x, sine 5x over x. But then you realize I need a 3 here and I need a 5 there, and you all should know how to get it. We're going to multiply by 1. We're going to multiply by 1. That 3 and that 5, they're both constants, and I have a rule. In a limit, I can pull a constant out in front. So I will pull the 3 and the 5 out in front, and I'm left with sine 3x over 3x, sine 5x over 5x. Now, both of those are approaching 0 in the same manner, so therefore that limit will be 1. And same thing here. 5x and 5x both approach 0, so by our theorem, that's going to be 1. So we get 1 over 1, which is just 3/5. A little tricky, but just learning that just because that and that both approach 0, shouldn't it be 1? No, they have to approach 0 in the same way, so I have to get them the same. So that's what's happening there. All right, derivative of sine and cosine. This is easy, kinda. Derivative of sine is cosine. Memorize it, know it, you'll use it all the time. Derivative of cosine is opposite sine. They just flip back and forth. But what you might forget is that minus. When is it minus? Is it for this one or this one? So I'm going to show you where the sine and cosine derivatives come from, and hopefully it'll help you remember. So this is a cosine function here, given a cosine. Now the slope right now, the slope of this line is 0. So the derivative is 0. As I move to the right, you'll notice the slope becomes more and more negative. That's why that graph is becoming negative. Right here, it's the maximum negative slope at -1. You'll notice from this point forward, it starts to flatten out, and it approaches 0. So at the bottom, we're going to get 0. Now as I move to the right, it's going to start getting positive, small and bigger. The maximum positive is going to be right there. But then it's going to start to flatten out, and it's going to drop back down to 0 there. As I move to the right, look, it's going to become negative, bigger negative, and it's going to flatten out. This will continue forever. But look, the sine wave usually goes like this. It goes up, down, up, down. This is doing the opposite. It's down, up. So the derivative of the cosine, the original black, is the opposite of the sine, because instead of going up then down, it goes down then up. So that's why the derivative of the cosine is opposite of the sine. That's how you can remember. Draw a picture of the cosine, look at the slopes, and you'll realize it doesn't produce the sine, it produces the opposite of the sine. Now, let me look at the sine function, and you'll see the derivative at this point right here, the slope is 1, so the derivative is 1. As I move to the right, it starts to flatten out and gets to 0 right at the top. Then, as I move to the right, the slope is negative, and it gets steeper, bigger, 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 negative there, which is a maximum slope of -1. And then it starts to flatten out as I move to the right and drops back to 0, becomes positive, maximum of 1, starts to decrease back to 0. And if you look at this function, that is the cosine function. So the derivative of the sine is the cosine. So that will help you with these. Now, here's what's going to start to happen to you. All these different things we're learning, you need to combine. And it starts to get overwhelming if you don't practice. We're going to do a lot of practice, especially when we get to the chain rule. We need to spend some time on that. But here is what you need to notice for the first one. We have a e to the 2x times a cos x. That is a product. You need to use a product rule. So dy dx or y prime. And we need to use the product rule. I kind of don't like what they're doing here. They introduced this last section where you have a 2x. You know the derivative of e to the x is e to the x, but what do you do with the 2x? They gave you a theorem, but I don't like that because you just memorize something that you don't need to. I wish they didn't do this, and I probably accidentally assigned some of those to you on the last homework, but I'm just going to tell you what it is. Don't memorize this because we're going to learn later in chain rule how to get the derivative of e to the 2x. So right now, we would leave the first alone, and you take the derivative of the second, but the derivative of cosine is minus sine, so I'm going to do that. Plus, and then you take the derivative of the first, I'm going to tell you, it's 2e to the 2x, and you'll learn in a future why. And then you leave the second alone, and they both have an e to the 2x, you'll see. So we're going to factor that part out, e to the 2x. We're left with minus sine x plus 2 cos x. And to make it prettier, we're going to put the positive 2 cos x first, then minus sine x. And that's the answer to the first one. Okay? And we'll continue and do we'll do all three of these examples for you. So let's do the next one. Let me erase this stuff here. Give myself some room. All right, you will notice another product rule, x times cos x. So you have to use a product rule at that point. So y prime, which is dy dx, is, now for the first one, I just take the derivative, and you should know derivative of sine is cosine. So that's easy. That's cos x. Minus, but the second part, I have to do product rule, so I'm going to leave myself some space. I leave the first alone, which is x, and I take the derivative of the cosine, which is opposite sine, which you will have memorized very shortly. And then I take the derivative first. Well, the derivative of x is 1, and you leave the second alone. Now I'm going to distribute the negative, so it's going to be plus x sine x, and then minus cos x. I hope you see it. The cos x's cancel, and we're left with a nice, beautiful answer of x sine x. That makes me happy. It's very simple. Now the last one, you should notice something. You should notice a quotient. Something divided by something. A high divided by a low. Therefore, to take the derivative of that, it's going to be a quotient rule. So quotient rule, it's low, so I copy the bottom, the low one. D high, the derivative of 1 is 0. Derivative of sine is cosine, so I'll have cosine x. Minus high, and don't forget to parenthesize it, the whole top one is high. Whoops. Let me fix that. That's ugly. Sine So high d low, well, the derivative of 1 is 0, and the derivative of sine is cosine, but I have minus cosine. So let me put opposite cos x all over low squared. Now on top, I need to distribute the cosine, and I have a double whammy here. This minus gets distributed, and the minus cosine gets distributed. We're going to do a double whammy. Let me double check and make sure I'm getting this right. I think we're good. Let me see. Low d high minus high d low. Okay. Let's go to the next line. So this and that will be cos x minus sine x cos x. Now the double whammy, that and that will become plus cos x. And then that and that will be another plus sine x cos x plus sine x cos x. Ah, look at that. Looky here. Ooh, now don't let me forget the denominator. That would be bad. 1 minus sine x squared. Now I'm excited because that and that will cancel beautifully. So on top, we end up with 2 cosine x's. On the bottom, 1 minus sine x squared. And I'll just leave it like that. You could change the bottom, but yeah, it's not going to help. You could do some crazy stuff, but it's not going to look pretty. The bottom becomes 1 minus 2 sine x plus sine x squared, or excuse me, sine squared. And that doesn't really do anything for me, so that was a waste of energy. The previous one's factored form, which we normally like to have our answer. So that is C. All right, more things that you just have to know. So we already went over the first two. The derivative of tangent is secant squared. You have to memorize that. And derivative of secant is secant tangent. That's something you just have to know. It's got to be automatic. Now, what's nice about these, all the cofunctions have negative for the derivatives. And so tangent is secant. Well, this is nice. Cotangent is cosecant. And secant is secant tangent. Cosecant is cosecant cotangent. So once you know the left side, the right side becomes pretty easy. So let me do this example. You should notice product, a secant times a cosecant. So we will use the product rule here. And just got to be careful. Let's see, y prime equals dy dx. We leave the first alone, and we take the derivative of the second. What's the derivative of the cosecant? Well, we just learned it. It's minus cosecant cotangent, but in parentheses, because I'm multiplying, minus cosecant x cotangent x plus, and now we take the derivative of the first one, but we have that. So it's secant tangent. And you leave the second one alone, so you have a cosecant x. Then, what do I want to do? I want to rewrite this. So I'm going to have secant is 1 over cos. Cosecant is 1 over sine. And cotangent is cosine over sine. Secant is 1 over cos. Tangent is sine over cosine. And cosecant is 1 over sine. And you might say, well, how did you know you're supposed to change them to a different form? It's just because I don't like cotangents, secants, cosecants. I like sines and cosines. And I'm thinking if I do that, it might make it prettier, and it does. You can try it. It might not help, but in this case, the cosines cancel here, and the sines cancel there, and it becomes prettier. Negative 1 over sine squared x plus 1 over cos squared x. And I like the positive one first, so I'm going to put cos squared first, and then sine squared second, and that is what I get. Now, if you don't like fractions and you want it even prettier, 1 over cosine is secant, and 1 over sine is cosecant. And so I think that's a prettier form. There we go. I want to do one more thing for you. Some of you might say, how am I going to remember all these? What happens on the test if you forget? Eventually, they're going to just stick in your brain, but we can rewrite tangent x is sine x over cos x, and then we notice we have a quotient. So the derivative of that would be low d high, and derivative of sine is minus cos, minus low d high minus high, I copy the high one, d low, derivative of cosine is sine. Oh, whoa, I just messed up, didn't I? Derivative of sine is cosine. And so low d high minus high d low, derivative of cosine is minus sine. That's embarrassing. Over low squared. So I end up with cosine squared x. Yoshida. Cosine squared x minus sine squared x, oh, dude, plus, because two negatives, I knew that. Cosine squared x, but the top by the Pythagorean identity is 1 over cos squared x, and 1 over cosine is secant, so that's how we get our secant squared x. So you could actually derive these derivatives by rewriting it as a quotient rule. That's the lesson for today. Bye.